So put simply, every radio system consumes more power than what it transmits. And this should make intuitive sense. If I'm transmitting a watt of power, my radio probably consumes at least a watt, but more likely a lot more than a watt. We define efficiency as the ratio of the transmitted power to the total consumed power. Think about if you have a radio like your cell phone, it's transmitting no more than 100 milliwatts, but it's consuming a lot more of that to display the screen, to do the digital signal processing, and to run the radio. So the DC power consumption is always much greater than what you're transmitting in any transmitter or radio system. And we can define efficiency simply as P out over P consumed, and as we stated, it's always below 1. So shown here is some recent results of a power amplifier. And I just want to recall, if we look at different architectures for radios, if we think about a quadrature radio with an I and a Q branch, and we bring these together and we sum them, and then we put this through a filter. And we've just mentioned briefly, there's usually an amplifier out here that drives your antenna. This amplifier is called the power amplifier. And what's different about a power amplifier from a regular amplifier is that the power amplifier strives to produce a large output power and to do it in an efficient way. What it gives up, most usually, is linearity. And so basically it tries to provide the highest output power and efficiency it can, and some of the trade-offs that it'll use are linearity is one of them. But obviously we want to try to transmit our signals with as little distortion or spectral growth as possible. So there's always a constant battle in a power amplifier between the efficiency and the linearity. And so let's take a look at this example here. This plot right here shows output power versus power added efficiency. Power added efficiency is basically just the efficiency of the power amplifier. And what we notice is that the peak efficiency happens at the highest output powers. And that makes sense because if I have a constant DC current being used by my system, or constant DC power, I get more efficiency the more output power I transmit, because efficiency, as we remember, is just P out over P DC. Okay? And over here on the left is a plot of the same PAE curve with the peak right here at this input power or this output power. Sorry. Or this output power. And this curve right here is P out. What we notice is there's a nice region where it's fairly linear, and then as we talked about before, it eventually saturates and we'll have our 1 dB point here. And so typically, if we want to avoid spectral growth and harmonics from nonlinearity, we're going to try to operate in this region where the amplifier is linear. And that would seem great, but if you look at it, that means we're limiting our efficiency to this range, where we could operate up here if we operated at peak power. And so this is the trade-off that I mentioned, is that the point of highest efficiency, which is right here, is typically not the point of highest linearity. And so for an amplitude modulated signal, we have to make a trade-off between efficiency and linearity, and we just bite the bullet and we operate down here because we can't handle that spectral growth and the harmonics that are created. However, there are some architectures, which we'll talk about in a minute, which can operate at a constant amplitude. And if they can do that, then we can pick any amplitude on this curve to operate, and why not choose this one right here, which would give us the highest efficiency. So why do we care so much about efficiency? Well, this is interesting. A report a few years ago stated that the total energy consumed by a radio base station, these are the cell towers you see around the country, is 1.2 to 2.1 terawatts per hour each year. This is equivalent to the electricity needed for 400,000 households. So you should be able to see right away that this isn't a small problem, that the power consumed by radio transmitters is quite significant, and efficiency is something that we should care about. From previous modules, we talked about nonlinear systems being operated in back-off to avoid undesirable effects such as spectral growth and intermodulation. And I just want to remind you what back-off is. If you remember when we talked about P in and P out, we did our curve and then it's saturated and we had our 1 dB point. And what we said is we're just going to operate in this region. And what that is that's backing off of saturation. So we talk about the region below the 1 dB point is operating in back off. So we're backing off the power from its 1 dB compression point. The output power is reduced, however, the overall power consumption stays the same, and that's why our efficiency drops in the curves we saw before. And the efficiency in the power back-off mode is obviously less than our maximum efficiency as we saw.